Good morning, everyone. Welcome to this webinar. We will start in less than a minute. Well, I think it's time, so let's start. So good morning, everyone. Welcome to this NISQ webinar. It's our last webinar, the last of a series of 9 we started back in November. So I'm Pascal Bernier-Bruna. I'm the communication leader for the NISQ project. And I will just share some practical information before I hand over to today's speakers. So this webinar is recorded and you will receive the link to the recording tomorrow. It's in listen-only mode because we usually have a lot of people registered, so it's a bit it would be a bit complicated to have everybody speaking. But however, of course you can ask questions. Just use the Zoom Q&A panel to ask your questions to the speakers. You will also see the questions asked by other attendees, and you can upvote or comment questions. And the chat is also open for a more informal exchange. And now I hand over to Dr. Venkatesh Kannan, who organized this webinar, and actually he also organized the other 3 webinars we had in February. And so he will be the moderator today. Venkatesh, are you ready?
Yes, thank you very much, Pascal, and welcome everyone. So as Pascal mentioned, today's webinar is the last of the series of 4 webinars in February. So we have as our speakers today, Dr. Arnd Hartmanns from the University of Twente. So his primary research focuses on tools and formalisms for modeling stochastic time and hybrid systems. Welcome, Arnd. And we also have Sebastiaan from the Leiden University. Sebastiaan also works in the NISQ project itself, where he's working on the use case associated with probabilistic safety assessment, quantum enabled ones. So the NISQ project itself is a 4-year quantum flagship project. It started in September 2020, and the consortium is composed of industry and research partners working in groups across several use cases. Broadly speaking, we have 3 categories of use cases: one around chemistry systems, one around quantum machine learning and optimization problems, and one around AI and graph algorithmics, in which the 4 webinars in February have been organized. So today's webinar is on the probabilistic safety assessment being enabled by quantum computing. So I'd like to welcome both speakers. And please feel free to keep your questions coming as the speakers are delivering in the Q&A session. So I'd like to hand it over to Arnd.
Okay, thank you, Venkatesh, for the introduction. While I start my screen sharing here. There we go. You should be seeing my screen now. I'm trying to get rid of the Zoom panels here. Okay, good. So thank you for inviting me to this webinar, and the title of my talk is on approaches to dependability, and I want to talk to you a little bit about how to model things in this area, what the algorithms are that are being used and to analyze them, and a little bit of advertisement of the tools we have. And I hope that in the end, for most of you, there will be parts that you already know and maybe parts or details that are new and that maybe you can use in your research in the project. So I am not a quantum person, I have to say. So in terms of questions on that, I will not be very much helpful, but I can explain all the details, of course, of the non-quantum things I've been doing, and then maybe you can think of where quantum helps. Anyway, the title of this There we go. The title of this webinar here was on probabilistic risk assessments. I was wondering, okay, what do I talk about this? And risk, of course, is a word that we all kind of know, but what does it even mean? So I just looked into a dictionary. Okay, what am I even talking about? I was saying, okay, I'm talking about possibility of loss or injury, and so on and so on. So possibility of bad things to happen. In particular, what I find interesting is that if you look at the definitions, then it even says, okay, this could also be related to the probability of such things happening. And well, also as students do, looking at Wikipedia, it also says this is the possibility of something happening and involves uncertainty. And to me, if you ask me, well, possibility is one thing, but I want to measure things. So I'm rather interested then in the probability of eventually at some point, some bad things happening. And I'm thinking about systems in terms of things that evolve from state to state, from configuration to the next configuration to the next configuration, either in discrete steps, if you have a clocked computer system, or in continuous time, if you have a cyber-physical system. And then we simply have a formula or a way of identifying what the bad states are. And we simply ask, okay, what is the probability to eventually get there? So that would be one way. But if you look a little bit into the definitions of risk in literature, some people also like to put it this way and say that risk actually is the probability of something bad happening times, well, how bad it is in some sense. So this is more like an expected value, expected loss kind of view on that. And now in this talk, I'll be focusing on this first part here. And then this here is a bit more difficult to say. I mean, in economic situations, it's pretty clear that could be the money you lose, but in general, what is the magnitude of a plane crashing or so? Then suddenly you need to quantify the value of human lives, and I'm not going to get into those kinds of things. So let's just stay with trying to calculate probabilities. And then my research actually is not so much directly in risk, but usually in dependability, but this is closely related to that, in that we're looking at things like safety of systems or the reliability. So this is the probability that we fail within a certain amount of time. And the classical thing is, if you ask, for example, if you operate a plane and you ask, will it eventually crash? Yeah, of course. If you fly it long enough, it will. So it's more reasonable to ask that will the plane or will my avionics system crash within the duration of a flight? Because after the flight, I can do maintenance, I can reset it all. I can ask other properties like availability. So I'm simply taking the integral over time, dividing it by time of am I in a bad state or not at a certain point in time. So I'm simply asking for the fraction of time that I am good or bad here. So I'm exchanging this a little bit, right? Every one of these questions you can usually turn around and ask for not only the bad states, but maybe being in the good states, and it's just one minus the other one usually. So here, this is a classic in performance evaluation if I want to know the uptime of my server. And closely related to the probabilities are rewards or costs. So I can ask what is actually the expected value of some kind of reward or cost I get. For example, I'm modeling electric vehicles, and then, well, what's the energy I consume? Well, and what is my goal? Well, the next time I could connect to a charger, because then the system kind of resets, I can charge again and start again. And can I survive up to that point? That relates to issues of survivability and all these kinds of things. In this talk, I'll primarily be focusing on just computing these kinds of probabilities with or without the time bound, but almost all the methods kind of equally with just a little twist work for computing rewards. So this is the outline of the next 20 or so minutes. And I simply want to give you a quick tutorial of the kinds of behavioral, so evolving from state to state models of these systems on the mathematical side. Also talk a little bit about how we then model them in a computer in a nice fashion. And for each of these, just give you a little bit of a feeling, what are we using them for some case studies that I've been recently working on. And in the end, give you a brief advertisement of the modeling language and the analysis tool set to actually compute these probabilities to give you optimal strategies and these kinds of things that I've been working on with several colleagues. So let's delve right in here and let me just talk about discrete time Markov chains. I would hope that this at the beginning is quite boring, that you have seen them well, maybe in your maths courses, maybe you've been working on them in related to the project. So this is simply, we're saying we have the evolution of our system. Here's a state that we've arrived in at some point, and well, what is the next state, the next configuration of our system? And it simply is randomly determined as a random selection out of a set of possible outcomes. So here I'm saying, okay, with half of the time I go here, 1/6 I go there, and so on. So I simply have the system as a sequence of discrete probability distributions as a discrete time, discrete stochastic process overall. I could have loops that makes the whole thing interesting. Otherwise, it's a pretty simple probability tree. And of course, it goes on, and typically have very large state spaces. I've been looking a little bit at, well, in my area, what kinds of systems have people analyzed with that? And I see lots of self-stabilizing algorithms. People have been working on digital circuits in here. You have unreliability in these, and a lot of work on communication protocols, as long as you can model them in a synchronous fashion. So a slotted communication, or you have a central clock that governs everything. And we should also note that, of course, a Markov chain like this, you can also simply write down as a probability matrix, saying that from the first state to the second state, you have a probability of 1/2, and so on and so on. And this allows you to mathematically manipulate that. Now, if we want to compute things like probabilities here, the simplest thing is to simply see where are we after I steps in the evolution. And we simply multiply our initial distribution. Here I'm saying in first state always with the probability matrix up to the power of I. So that simply means, and maybe that is a little bit interesting to see if you can do quantum things here, we simply need to do matrix and matrix spectrum multiplication. Now this is a bit too simple to analyze interesting properties. So we're more, what have we have to do if we want to get this risk kind of style computation, probability for something to go wrong eventually? Well, we could have this tiny little DTMC here as an example. What we have to do is simply solve a linear equation system. So in essence, an equation system involving the probability matrix. Here I've written it down explicitly. We're just calculating this value for every state. So for the first state here, x as state 0, this is the value that we have, and you simply see that it is the structure of the Markov chain that goes in here, or the probability matrix if you want. And we can solve this system via various methods. You can do it more or less exactly through Gaussian elimination. You can use various iterative, approximative methods to solve that. You get the probabilities you want here. Now, in practice, it turns out, I mean, we rarely use Gaussian elimination because it doesn't scale. We use iterative methods. In particular, one that we could use is value iteration, and that also works for DTMC. So we start with an under approximation of the value we want. So clearly, the probability is 1 for our goal state here. I mean, I'm coloring it green. It could also be the bad state, and I should have colored it red. So for every state, we start with a lower bound on the values we want, and then we simply step by step iterate these. So we're doing one-step probability updates, so you're getting higher and higher values over time, and in the end, at every step you have the probability to, in at most I steps, get to your goal or non-goal or bad states, and the least fixed point is actually then the eventual probability. The only problem here being, and I should note this because many people ignore that, is that we would want a certain error. We want the difference between the true and the computed value to be below some epsilon, but we don't really know when to stop this procedure. If really the unbounded horizon thing is what we're after. So classic value iteration can't do that, but there are modifications that also compute upper bounds with some complications, and that can give you really an interval of where the true value must lie. Then also you need to look at the floating point inexactness and these kinds of things, but in principle you can you can do an epsilon correct solution for those iteratively, and this really scales to large systems. So if you do this in a modern probabilistic model checker, I think nowadays about 100 million states is what you can do explicitly without complicated compression methods. Good. And a little application here that I find quite nice, driven by colleagues of mine from Utah, is that they've been looking at network on chip routing. So they've built a small model of a small network on chip of 4 processors and 4 routers, each with queues forwarding packets. They looked into different generation packets, like bursty packet arrival here, and very regular packet arrivals, like every second tick of the clock you have one. The destinations they assume are random. That's why it is a discrete time Markov chain. So that's where the probabilities come in. And there's a fixed routing policy. And this means that a Markov chain actually suffices. There are no decisions to be made anymore. Everything is stochastically determined, and it's all randomness in the outcomes. But this is already quite difficult to model in a way that we can analyze it, that we can compute these probabilities. So they, if you look into the paper, there's a sequence of abstractions of getting rid of details to make it tractable in the end. And what they were then able to do was they were looking for certain traffic patterns, especially strong changes in how full the queues are and what the routers have to do, because these induce noise in the power supply. And that's something you want to avoid in general in these kind of circuits. So they were looking here for the probability as you increase the number of clock cycles. You're looking at the probability for certain of these events. So for one such event, or for 10, 20 such noise events to occur. And they could compute it for different kinds of events. And that's what a probabilistic model checker. So a tool that builds the state space of all of these and does a calculation, value iteration on the whole model to give you more or less epsilon precise results can do. And then you can simply get like the cumulative distribution function like this. So that's all I wanted to say. If you're really interested, please ask me some questions, or also have a look into the paper from last year on this example. We also use statistical model checking, so Monte Carlo simulation here. That's something you can do for Markov chains if the state space is simply too big to be represented in memory at the cost of statistical imprecision through the sampling. And especially if you have rare events, this becomes very problematic. That's already all I wanted to say on Markov chains, because they're all stochastic. So in some sense, they are quite boring. It's simply a probability calculator if you work with these. What I find more interesting is if you actually have some optimization choices in there, and that's when you go to Markov decision processes. So then again, we are in a certain state of our system, but now we have a choice. We can do action A and then behave like a DTMC and end up somewhere, or we could choose a different kind of action and then go somewhere. And this could be, and then of course we go on and on. So we first have this non-deterministic choice, and then we have the random choice of where we actually end up, what the outcome is. And in particular, these non-deterministic choices, we interpret what they mean. They could be controllable, and then we might want to find the optimal control to get the lowest probability of reaching a bad state. They may be uncontrollable. It may be an adversary that plays against us and tries to break our system, especially if you have a security perspective. And then we would ask, like, well, what is the worst case outcome? If they perfectly attack our system, how bad is it going to be? People also say this is a 1.5 player game. The half player is randomness. Yeah. So they are used a lot in machine learning, the classic probabilistic planning model. So robot scheduling is one of the standard examples that people are using. But in essence, all kinds of reinforcement learning, deep learning things, they foundationally build upon the notion that your system can be represented as some form of Markov decision process. And that's how they're more or less correct, at least as long as you leave out the deep part. And if you have a concurrent system, if you have agents or components running in parallel with different speeds, you need these, because then you need this interleaving of you don't know who goes first and who is faster than the other. And that's when you need these choices of component A goes first or component B goes first. You don't know, you simply take into account all possibilities. So The problem here, of course, is there's no more single probability for something bad to happen. You simply have a range of probabilities depending on how you do these choices. Do you always do A? Do you always do B? Do you do A half the time, B half the time? Or maybe after 3 steps, you change your decision. So you have an optimization problem. And in particular, I like to visualize that you have this range of probabilities, and somewhere is this range of achievable probabilities in there. I should say that there exist tools, especially if they use simulation, that do some kind of random choices over here. And that, of course, we have to keep in mind that that only gives you some results somewhere in this interval. But of course, if you have an attacker, you want to know what is the best they can do. Or if you want optimal control, what is the minimum probability of getting into a bad state? So to analyze them, I don't want to say much, just mention that you can use the same kinds of equations, but now it's optimization. So instead of linear equation system solving, you go to linear programming, which in particular means that for unbounded probabilities, this is a polynomial time problem. And you can adapt value iteration. You simply get an additional max operator if we're looking at maximum probabilities, or a min operator if you're looking at minimum probability. And value iteration actually is worst case exponential time, but in practice, it works better, and that's what everyone's using. You can also use policy iteration. I think some people call it Howard's algorithm, which is that you iteratively improve the choices. So you start with saying, okay, I always do A, and then you may figure out by looking at the DTMC that happens if you get rid of the other choices, see what is the outcome, improve your choices, and then do this in a fixed point computation. Good, just to give a brief hint. And my favorite recent application of that was that we were looking at constellations of small satellites orbiting the Earth, so small cheap components, and we want to get a message from some ground station to some central ground station. And this was with colleagues in Argentina. So of course, the central ground station was in Cordoba. And that means that these satellites, they orbit the Earth, and then your data is uploaded when one satellite passes. And at some point, the paths of two satellites come near to each other. And then you may transmit the data to the other one, and then it goes around. And at some point, it is in range of the base station. So you have your data hopping around from satellite to satellite, but it's wireless communication. You sometimes may lose your data, so you have a delay tolerant network, what it's called, but there's uncertainty in there. And what we want to do is we don't want too many copies of our message, because these are very cheap, simple satellites. They're constrained in memory, and you need to store your messages for a long time, but we want the highest probability of the message to eventually arrive at the goal. And we can model this kind of abstractly, because you can pre-plan when are the contacts, you can discretize this all, and you can estimate the probabilities of communication, and you get an MVP model out of this. And then you can just simply ask, okay, what is the highest probability to get there, and what actually is the strategy? Do I send my message here, here, and there, or do I send it here and then there? What is the best thing to do? Or if I have 2 copies, do I send both here? Or do I keep one and send the other one over there? Or do I keep that one and send it over here in the end? And the complication of all of this is that this is in fact a problem with the distributed information. Whereas if you do classic MDP analysis, you have a global state, and there exist partially observable MDPs, but they won't help you here, because it's multiple distributed components with different views, which is not captured by classic POMDPs. And here you can see that this is, if you decide to send your 1 copy over here and here, then what do you do here with your 2nd copy? If this failed, then that's where you want to send it. However, if this one here has a copy of the message, there's no point in sending your other copy to that one as well. But you can only know that kind of if this satellite knows the state of this satellite, which is not what happens in practice, but an MDP analysis would optimize with that knowledge in mind. So we had a paper on that 2 years ago at NFM of how to actually be able to do that without doing these unrealistic kind of strategies. We built a model of this system in the modest modeling language. I'll come back to that in a moment. And then it turns out we actually used a variant of statistical modeling of Monte Carlo simulation, augmented to deal with the non-determinism in a certain way to try to approximate these realistic strategies in there. Again, happy to answer more questions on that. And that's already on MDP. And we're going very quickly through these. I hope to just give some inspiration there. My more favorite model in the end actually would be the one of Markov automata. And I guess probably many of you have heard of Markov chains, Markov decision processes. I guess most of you haven't heard of this yet. And what is this doing? So it's taking MDP and combining them with continuous time Markov chains. Because so far we had no notion of real time in there. We had just had this stepwise evolution. You can say that one step is one time unit in some way, but that's not necessarily a very useful way of dealing with time. So CTMCs allow you to do that explicitly. So here's an example of a Markov automaton. In these, you have two kinds of states. So you have probabilistic states, like the orange one here, that behave like in an MDP. No time elapses in general, unless someone blocks your, someone else blocks your actions here. And then you go to random outcomes, and you can make an optimistic choice. And the other states, these are the ones with dashed transitions going out, or what we call Markovian states. They are like in a continuous time Markov chain. So here in state number 3, you have one outgoing transition with rate 2, no longer probabilities, but rates. And this means that you spend some time in state 3, and that's a random amount of time. And this amount of time follows the exponential distribution with rate 2. If we had 2 outgoing ones, and here's another one with rate 3, then the time we would spend here would be exponentially distributed with rate 5, with the sum, so the exit rate of this. That's what happens in the CTMC. And the nice thing about Markov automata is that they are widely used for various things. You can do performance optimization. So where CTMC are classic in performance evaluation, with Markov automata, you can optimize performance of things. I'm also mentioning, since the second talk is on fault trees, if you go from static fault trees to dynamic fault trees, where you have spares and repairs and these kinds of things that evolve over time, then Markov automata are the standard semantics of a dynamic fault tree. And then you can convert the fault tree to a Markov automaton, put the Markov automaton into a probabilistic model checker, and then get results out of that. And you can especially do that in a compositional way. So you can have, again, an agent or component-based system, and then have a Markov automaton representing the semantics of the two things running in parallel. That is not possible so easily with CTMC, and that's not possible with the naive combination of the two continuous time Markov decision processes. So the analysis, well, if you have no time in your query, that's easy, but the interesting thing is what if you have a time-bounded reachability. I'm also looking at my time-bound, so I'm just aware of that for the moderators. This is interesting because for one state, well, you can look at the exponential distribution and you know what your probability to stay a certain amount of time in there is. But for the optimal Markov automaton, your optimal choices depend on how much time you have left. So we had this example here where, let's say we want to go down there, and you have a kind of safe but slow route here with many delays. So you see it's 2 and 2. Or we have the risky route down here where it's quite fast, only 1 delay of on average 2 time units, but you may just get stuck in here. And then, so depending on how much time you have left, different choices are the optimal choices here. So you see that at this, if you have more than 0.67 time units left, then yeah, sure, go for B. But if you have less time, well, you need to risk A. And there's 2 competitive algorithms nowadays doing that based on uniformization and adaptive discretization of the time horizon. Good. Little case study. We were trying to break Bitcoin with a well-known attack to try to do double spending. The nice thing on Bitcoin is that it is kind of self-adapting to have about 10 minutes average time to add a new block to the blockchain. In practice, when we did the study, it was more like 12 minutes. So this ideally can be modeled as a continuous time Markov chain-like thing, because it's really random. Sometimes it's fast, sometimes you need a long time, but on average it was 12 minutes. And you want to kind of fork the blockchain on your own if you control a large amount of the hash rate. And the question here is, when do you keep extending your own secret fork? You need that to be longer than the main fork everyone else is working on. And when do you restart? Earlier work did kind of a manual analysis of different strategies and found an optimized one that told you, well, if you actually have controlled 20% of the global hash rate of Bitcoin, which was the case for certain pools at that time, then you just need a few days and then you can do double spending. We built a Markov automaton model, and then we could really synthesize the true optimal strategy on that. And so we built a modest model like this, and we got a result like this saying here, well, the optimal strategy is, and then we have a certain amount of conditions. Looking at my time bound here, I would like to go quickly, and we can come back to that if you have a question, because I would just like to do a little bit of quick advertising. I'm saying all these things. You've seen this modeling language thing. So I'm actually in my research working on a high-level language to build these kinds of models for Markov chains all the way up to stochastic hybrid systems. And that's described in a relatively old paper by now and available online. And it's actually supported by a set of tools that can do model checking, Monte Carlo simulation with rare event simulation in it, probabilistic planning, safety verification for hybrid systems. And there's also a few support tools, so we can convert between this language and the standard format that other tools have been using, the Jani format, which is a JSON-based format. We can visualize these, we can export to Python. I'm using this in lectures in my master's course, so students can actually implement their own model checker in Python when they're learning about model checking algorithms. And nowadays, all of this is integrated into a nice IDE inside the Visual Studio Code IDE. So here you're seeing a screenshot that I've been using from my course. And there, in essence, they're learning about the whole chain from model checking to simulation in the end. And I was very happy that I was able to replace MATLAB Simulink by the integrated simulator in here. And they work on battery models at the end. With that, I would come to the end. I've given you a very, very quick tour through a bit of risk dependability, focusing on probabilities, but most of the things and algorithms I mentioned are also applicable to expected accumulated rewards. We have this family of models that I've walked through a little bit, give you a hint of analysis algorithms. There's many applications, of course, not just the three I mentioned, and people in other fields are, of course, using Markov chains for entirely different purposes. And that's the pointers you would need if you would like to look at more things. And with that, I think, I'm not sure if we take the questions now, I think we take them later, but I would be happy to hand back control. Thank you.
Thank you very much, Arnd. That was really interesting to understand the classical and the foundational aspects of risk assessment and then modeling. So you're right, we'll take the questions at the end together. I don't see any yet, but please feel free to keep them coming. Following up, Sebastiaan, welcome. So Sebastiaan would be talking about quantum speedups for classical probabilistic queries. So over to you.
Yes. Yeah, so I hope everyone can see my screen.
Yes.
Yeah, so specifically, I'm going to talk about speedups in fault tree analysis, quantum speedups in fault tree analysis. This is work done as part of this NEASQ project, also in collaboration with EDF, which is an industry partner who uses fault trees to analyze their own systems. So fault trees are used to model how failures propagate through a system. In industry, they're used to analyze, for example, risk in airplanes or power plants or data centers. And what you can imagine is if I have some system, let's say an airplane, and an engine fails, that doesn't necessarily mean the entire system is going to fail, right? So an airplane might be able to land safely with just one functioning engine. And we want to investigate like small subsets of components or events, which if something goes wrong, they can trigger a critical failure. Yeah, so that's what I'm going to talk about in this talk, and then I'm going to show how we can use quantum algorithms to speed up finding these subsets. So starting with a definition of fault trees, they're technically not trees. They're directed acyclic graphs. The difference with trees is that in trees, nodes cannot have common ancestors, and in DAGs they can. At the bottom of the fault tree, we have the leaf nodes, which are basic events. So these are right. If you think about modeling risk in a system, these are small events or small system failures as part of the larger system. Then the internal nodes of the graph are Boolean logic gates. So for example, AND and OR. And there's a single root node, which is the top event. And this usually captures some critical failure of the system. And then usually with each basic event, there's either a probability or a probability distribution associated. So what information do we want out of these fault trees? We can kind of split this up into two parts. So these are either qualitative measures or quantitative measures. In terms of qualitative measures, this is what I already mentioned in the beginning. We might be interested in the minimal set of events which can cause some critical failure. Alternatively, we might also be interested in a minimal set of subsystems which can keep the system operational. These are kind of each other's opposite, these queries, but they're not each other's complement. Yeah, and when we go to quantitative measures, right, as Arnd already said, this goes more in the direction of we include these probabilities and a time model, and we can ask questions about, right, what's the probability that the system fails within a given time, or the percentage of time that the system is operational, or the average time between failures. Yeah, so we're interested in, as I said, these sets of events which can cause a critical failure, which are called cut sets. And specifically, we are interested in minimal cut sets. And the cut set is minimal if no subset can be removed while keeping the top event true. So as an example, A, B, and C here, this is a cut set, because if we set these values to true and C, right, we evaluate the circuit, then the top node evaluates to true. But this is not a minimal cut set, because we can remove elements. For example, B and C is also a cut set, and therefore A, B, C is not minimal. In this case, for this particular example, A and B and B and C are both minimal cut sets. The reason why we are looking for small cut sets is because we want to find sets of events which have a high probability of causing some critical failure. And it turns out in practice that finding small sets is a good approximation for finding sets which have high probability, even if we completely disregard these probabilities in the analysis. In theory, yeah. So how hard is it to find these cut sets? In theory, finding a cut set is NP hard is finding cut set simply reduces to circuit set reduces to finding cut sets. However, in practice, for many practical instances, finding a cut set is easy. The difficult part is to find the smallest minimal cut sets. Current methods which are used in industry, they are limited in the size of fault trees they can handle. So most of industry methods are using decision diagrams, which I don't want to go into too much detail how they work, but basically you take this fault tree, which is some graph structure, and you generate a different graph structure, which is called a decision diagram. And from this decision diagram, you can read out all the cut sets fairly straightforwardly. But the drawback is that in the worst case, this decision diagram becomes exponentially large in the number of basic events of this fault tree, which means you need to have an exponentially large data structure in memory. So to this end, we are going to find cut sets with set-based methods. A set formula, specifically in a conjunctive normal form, can be obtained from a fault tree using a specific methods. This is fairly textbook. Basically, what we can do is we can introduce a number of new variables. So this fault tree starts out with 3 variables, 1 for each input node, and then we can kind of build a CNF formula for this fault tree, which will be at most will have at most size polynomial in the number of nodes in this fault tree. So this formula might introduce new variables, but it will never be more than polynomially large in the size of the input fault tree. So this idea of moving to set is not new in non-probabilistic model checking. This has been used very effectively, and more recently this has also been applied to fault trees. So not in a quantum way, but classical methods which use this translation to set. Yeah, so the benefits of doing this classically is that these set solvers, they don't suffer from the same memory bottlenecks as decision diagram based approaches suffer from. And the quantum advantage is that we know how to obtain quantum speedups for satisfiability. So this is an overview of our approach. On the left, we start with a fault tree as input. This gets converted to a CNF formula. And then we add a constraint, which basically says at most k basic events can be true, and where we start k equals 1. This constraint can be added within the CNF formula itself. So you obtain a new CNF formula, which is slightly bigger, but now can only be satisfied if in cases where k basic events are true. Well, then we solve this CNF formula either with a classical set solver or with Grover, and we find a satisfying assignment if one exists. And from this satisfying assignment, we can extract a cut set. And if we are interested in finding more cut sets, we can block the cut set we have found. So this basically updates the CNF formula in a way that the cut set which is already found will not be found again. And this loop is repeated until either enough cut sets have been found. or there are no satisfying assignments left. And if there are no satisfying assignments left, but we still want to find more cut sets, then we increase k and then repeat this loop again. The advantage of doing it this way is that if we start iterating over k from 1, we block all the cut sets we find. This guarantees that all the cut sets we find are in fact minimal cut sets. The reason is that, for example, once k is 5, we know that all cut sets which are smaller than 5 have already been blocked. Yeah, so I now want to spend some time to explain how we can encode this set problem in Grover, starting with a general explanation of Grover, and then going into how to encode sets. So this might be familiar to people who are familiar with quantum. Grover's algorithm starts with n qubits as inputs, where every qubit corresponds to one of the variables in your CNF formula. And then there are a number of ancilla qubits. All the input qubits are brought into a superposition. And then this so-called Grover iteration is repeated O square root 2 to the n times. This Grover iteration consists out of 2 parts, which is a call to an oracle and an inversion about the mean. What this oracle does, it basically flags every satisfying assignment in the formula. So how do we encode a set formula in a quantum circuit? Here up, we have a CNF formula. What do we do is for every clause, we implement a set of gates which checks if the clause is unsatisfied. So this set of gates kind of implements the complement of this clause. And we do this for every clause. And then at the end, we can check whether none of the clauses are unsatisfied, which is the same as checking of whether all of the clauses are satisfied. Then we have some uncompute step, which is necessary to keep the entire computation reversible. And what we have in the end is that this qubit B is set to 1 if and only if this assignment over x1, x2, x3 is a satisfying assignment. The trick, of course, is that this entire thing works if you just input binary values for x1, x2, x3, but we can also input a superposition of inputs, and then the entire circuit acts on a superposition. This particular example uses one ancilla qubit for every clause. It's fairly straightforward to reduce the usage of ancilla qubits to something which is logarithmic in a number of clauses by instead of checking every clause individually, what you can do is you can keep track of a counter. And then you simply count the number of unsatisfied clauses. And if there are no unsatisfied clauses, then do a split flip. It can also be reduced to a constant number of ancilla qubits by encoding number information in the phase. This is somewhat more complicated. Yeah, so that brings us to the next question. Is Grover actually helpful compared to a classical set solver? So people who know things about classical set solvers might have already recognized something here. So if we want to solve SAT brute force, we take 2 to the n steps, where this O star means that we're omitting polynomial factors for simplicity. Grover does this in the square root of this time. However, the best known classical algorithm has a worst case performance, which is better than Grover. So it seems like we might not be quite there yet. However, it turns out that it's possible to implement a quantum version of this QPSA algorithm, which achieves this this Grover-like speed up over QPSA. This is something which is also related to previous work from Leiden, in which a divide and conquer approach is presented, where basically if you have a quantum computer which is not large enough for your entire computation, then you want to split your problem up in such a way that your sub-problems can run on the quantum computer, and you're still able to achieve this quantum speed up on these small instances. But then you still need to be able to tie to combine all these sub-results to get an answer to your original problem. Yeah, so I went through this a little bit faster than expected, but I think it's fine. What I've talked about is fault trees are used to model failures in systems. In theory, we can obtain quantum speedups by translating the problem to a set. And we have this this quantum version of this best known classical set algorithm, such that we can still obtain a quantum speedup over that. Possible future work can go into the direction of including these probabilities, which means having a quantum version of weighted max set. So last year there was this paper which looks at, among other things, it looks at max set, but not a weighted version. So this might be something interesting to explore. I think that's everything I have. So thank you for your attention.
Thank you very much, Sebastiaan. I believe we have a few questions as well. So the first is from Colin. The question is, what is x4, x5, x6 in this SAT formula?
Yeah. So basically what happens here is for every gate, for every output of each gate, a new variable is introduced.
Pascal, I believe we have the question time slides shared now in place of Sebastiaan's.
I can explain it without my slides. So basically, these.
Sorry.
Well,
you can take back control. You can share your slides again. Sorry.
So basically, what happens is for every output, what these Zeiten transformation do is for every output of each gate, a new variable is introduced, and then clauses are introduced such that this output is true if and only if the logical operation on the inputs is true. So this is where these x4, x5, x6 come from. They're the outputs of these logic gates.
Thanks. I believe we have a question for you, Arnd, from Emil. So the question is about comparing the modest toolkit with the more generous generic probabilistic languages in Stan or Pyro or PyMC3. Do you have any comments on that?
Yeah, so thanks. That's a very interesting question that I was just preparing an answer to. So in essence, these languages are what they call themselves probabilistic programming languages. So that's what they're going into. And that's kind of a, yeah, that's an interesting area because there's a lot of research in that area at the moment. And so probabilistic programming typically is more about inference, about writing down your behavior. You sample from certain distributions, you modify your data, you sample additional data, and then you can have a program-like structure that deals with sampling statements, and then in the end you typically make a conditional statement saying, okay, assuming this is the outcome, what was the input distributions or things like this. And so this is a slightly different, but of course very much related problem to what I've been looking into in terms of computing the probability, finding the strategy for these things. Now, the main differences conceptually are that probabilistic programs don't have to correspond to finite state Markov chains or stochastic processes or things like this. So they can be something with infinite computations. Then of course, like questions like termination are interesting. And well, if they do correspond to a finite state thing, typically you can encode them as a Markov chain, Markov decision process, as long as you don't have the conditioning, and put them into that model checkers like we're dealing with. So for example, the model checker Storm from Aachen has a module that converts a certain simple probabilistic programming languages into, well, for example, the Jani format that in turn I can import. In terms of the languages, looking at the ones you mentioned, I think my impression is that these probabilistic programming languages are very much focused on data, so that you can easily import large sets of data and then do sampling on these. And in some way, it also combines the analysis and the model in a little way. Some of these, I think, was it Pyro, have it quite separated. The others seem to me, from a first glance, to have a bit of the two things more easily intertwined. But especially, it seemed to me that they are focused on dealing with data, whereas a language like Modest, stemming from process algebra, is more focused on behavior, in the sense of saying, okay, my system is composed of 5 agents running in parallel, and the behavior of each agent is to have a choice between this, then a probability to do that, and so on. So I think that's a kind of different perspective to rather similar things in there. Yeah, and of course, one difference is that the main focus of Modest is actually to go beyond Markovian systems, so to go to systems with a non-Markovian time, but especially also to stochastic hybrid systems, which I don't think is something that's typically in a probabilistic programming language. I think that's how I would phrase it, but it's very closely related things.
Thanks for the question, Emil. I hope that gave you some clarity as well. We have a question from Alphonse to Arnd again. Is it possible to phrase the analysis of NA and the other models as a linear equation system? So he's asking this because this would allow him to use standard quantum algorithms like HHL to get a speed up in some cases.
So of course, the linear equation system analysis stops as soon as you add the non-determinism, because then you are in an optimization problem, and not just in solving an equation system. So that in essence stops for DTMCs, for continuous time Markov chains. And also for continuous time Markov chains, you would want to use uniformization. So that's more solving, computing the truncation of an infinite sum of solutions to linear equation systems involving the Poisson probabilities that you use to cut off things there. So I think the basic answer would be, well, as soon as you go to systems with non-determinism, you're beyond equation systems. You are in optimization problems. Not sure if that's the answer, but just let me know.
Thanks,
Of course, you
Arnd.
can represent an MDP still as a matrix. Then you have different, you don't have state to state, but you have state and action. So you're it's not a square matrix anymore, but then on one hand, you have this state with this action goes there, this state with this action goes there, a bit like the Q functions in Q learning. So, but still, it's not about solving the equation system now.
Thanks, Arnd. I believe we have a question from Quang to Sebastiaan. So the question is there any gain in using a hybrid approach of using both a classical SAT and a quantum Grover, for example?
Yeah, so this is an interesting question. So using Grover on its own, as I've briefly shown, is actually slow. If you use Grover on brute force, on this brute force approach, so if a quantum version of this brute force set solving, is actually still slower than the best known classical algorithm. You can implement this quantum version of this PPSC algorithm. So this is in a way kind of like a combination of this classical set-based approach and Grover. I'm not sure in what other ways you could combine them. Yeah, I hope that sheds some light on it.
Let us know, Quang, in the chat if that clarified your question. We have one more from Yusuf. I believe again it's for you, Sebastiaan. How can we scale the SAT in a quantum circuit, and what problems can then SAT solve?
Yeah, so I'm not sure what you mean by scale. So Grover itself is an exponentially deep quantum circuit. So this is something which is not so easy to run on like noisy quantum computers. However, if you have something which can run Grover, encoding SAT scales relatively well, as in both the depth of the quantum circuit and the number of qubits you need are both they both grow at most polynomial in the number, like in the size of your SAT formula. In the best case, you can, I think, achieve that both of these, the depth of the circuit and the number of qubits, grow linear in the size of the SAT formula or better. What problems can SAT solve? This is the answer. This is basically everything. SAT is like the NP complete problem. So every problem in NP can be reduced to SAT. So this is why it's very it's a very generic way of solving problems, translating it to SAT and then solving the SAT problem. For our case, we're not just doing the translation to SAT because then we can solve it with Grover, but we're also we also have like good reasons from like the non-probabilistic domain where this translation to SAT works really well. But in theory, almost everything can be solved by translating it to SAT.
Thanks. We have one more question from Mohammed in our own project NISQ. So it's a question to Arnd. What is the size of a tractable instance for the problem of reachability in the best known algorithms?
So yeah, thanks for that. My favorite question. So first question is, how do you measure the size of the tractable instance? Of course, if you have a high level model, that can be a very small model that expresses a very large underlying state space. So I would typically answer this question in terms of the size of the Markov chain, the size of the Markov decision process. I hope that's okay for you. And then I would say, okay, if you use a relatively simple approach, so an explicit listing of states in memory and transitions, and then doing the calculations on an explicit vector of doubles or so, then I would say for Markov chains and Markov decision processes, with typical computers today, like it's your memory bound, right? So the most important thing is how much memory you have. And if you have 16 to 32 gigabytes or so, you can do a 50 to 100, maybe 150 million states. Of course, if you have a system that has very dense transitions or very many probabilistic decisions, then you can have fewer states because you have more transitions to represent memory. But roughly, this is what I usually see, that after about 100 million states, we start running out of memory, and then you're swapping, and then you can forget about the solution time. But this is for the naive approach. And of course, most of the research in this classic model checking area is about how to deal with larger systems and do intelligent things for them. So one approach is to use binary decision diagrams to represent the system, maybe also to represent the solution, but that's a bit difficult because of the floating point numbers in there. And then, of course, there are well-structured examples that go up to whatever ridiculous numbers, like 2 to the power of 100 states, that you can represent in a very small binary decision diagram. You can use by simulation minimization that gives you a larger state spaces. But then, of course, it all very much depends on if your model happens to be suitable for these kinds of methods or not, and that's not always easy to predict. So now you're asking about systems with components. That's, of course, is a lot more difficult to answer, because I mean the classic tools in the end always go down to constructing some representation of the flat state space. So if you add components, you have an exponential increase in the size of your state space, unless they synchronize very tightly, then you can even reduce it. So that's very difficult to predict. I would say that if I look at my tools, they're a bit limited in that they do the composition of components kind of at runtime. They don't do it at the beginning, but while exploring the state space, they keep the component structure so that you don't get an early explosion, and then you're a bit limited in time. The more components you have, the more complicated the exploration becomes. And then I would say you're getting into whatever 5, 10, 20 components, depending on how complicated they are. But this is less of a fundamental limitation as more of an implementation limitation. I think there are agent-based simulation tools that allow you to do huge numbers of these things, but then they do simulation. So that's difficult to answer. Let's see. Hope that helps.
Thanks, Arnd. Thank you very much, Mohammed, as well. So those seem to be the questions for now. Would Arnd or Sebastiaan have observations between each other in terms of what you have seen in terms of the presentations and the work?
Yeah, Sebastiaan, go ahead.
Well, I did have some questions. For example, one of the things you mentioned was that this value iteration was worst case exponential, but that works well in practice. Do you have any intuition why that is?
Well, one thing is that I don't quite remember what was the cause for the exponential time. In many cases, these exponential arguments have to do with the encoding of real or rational numbers, and then that's a bit stupid because then in practice we're using floating points, and you don't actually feel that exponential part. Also, I was showing these cumulative distribution functions, and actually computing those things in principle also gets you into exponential time, but actually it's pseudo polynomial. So I mean, I don't care. To me, that's as good as polynomial time. But I don't have a clear intuition of why it works. Well, I mean, the comparison, for example, could be to linear programming in Markov decision processes, right? But also in linear programming, it is a polynomial time problem, but people use the exponential time algorithm. They use the simplex algorithm or variants of it. And it just happens to work much better than the polynomial time solutions. But even then, I think linear programming is simply a much more generic solution. And the solvers are not made to specifically very efficiently represent these large state spaces in memory. You're kind of duplicating your memory requirements by encoding everything. So I think that's why we don't use them, but instead we use value iteration. And typically value iteration simply just goes very quickly from your lower bound to something rather close to the true solution. You can build adversarial examples where for example, you go to a new state with a low probability and you loop back to yourself with a very high probability. And that means that on every update step, only a tiny little bit of probability propagates forward through your state space. And you need to run a lot of iterations until you actually get the probability from your goal propagated all the way to your beginning. If you have these, value iteration can be quite slow. That may well be where the exponential effect happens if you have a chain of these things. But in practice, we don't see these that much. And then there are methods to get rid of such loops that get rid of the problem.
I see. Yeah, is there anything which stands out that it's also like intractable in practice? Because right, many of these problems are then theoretically intractable, but in practice, like efficient tools can still handle large instances. Are there any specific problems which stand out that many practical instances are also intractable?
You mean practically intractable,
yeah.
Right? So I don't think there are really, at least in the work I've been coming across, that there are case studies that pose a fundamental problem to the whole toolkit of techniques we have. The problem is always simply that your state space, your model gets too large, and then you run out of memory. And that's simply that at some point you reach the threshold of how much you can do. That's not a really fundamental thing. And of course, you have the exponential blow up in the state space explosion problem. So you very quickly go there. But in principle, with enough memory, yeah, you can do this all. And I mean, there's very many complementary techniques. So I was mentioning rare events. If you are trying to calculate a very low probability, then the simulation-based approaches fail. But of course, then typically these cases are small, and we can use the model checking-based approaches. Whereas if you have a Markov chain, which is not a rare event, well, and your model checking fails, you can do the simulation-based perspective. So actually, I think there is actually, for most things, you can switch around. The fundamental limitations, I think, are going beyond Markovian systems. So having non-exponentially distributed things, because then you run into undecidability very quickly instead of untractability. So in some sense, it's quite boring. You simply need to have better tools that work better for these things. That there's not so many fundamental open things in there anymore, I would say. Unless you go to more expressive models, hybrid systems, then yeah, there's lots of stuff still to be done.
Thanks.
Fundamentally. So I mean, I would of course be asking this the standard question that probably has a simple answer of have you considered dynamic fault trees?
So far we have not. This is yeah, I mean, this adds a lot of complication, of course. So this is something definitely we want to explore in this direction, but so far we have not done this. No, I know there's some quantum algorithms for example, speedups in finding steady states in Markov chains. But then again, if you move from Markov chains to Markov decision processes, it's already very difficult to use quantum algorithms for these things.
So this is what actually I would be interested in knowing about pointers of where quantum things have been applied and could maybe be extended a little.
Yeah, I don't currently have a literature overview ready.
No, but we take this offline.
Yeah.
Yeah. I think we're giving back the word to Venkatesh here, right, Sebastiaan?
Yeah.
Almost. Yeah. We have a comment from Mohammed as well. So he says, dynamic fault tolerance is a good candidate to solve some of the dependability problems due to quantum walks. In any case, so thanks very much, Arnd and Sebastiaan, for answering all the questions and for the very interesting presentations. If we do not have any other questions, then I'd like to thank everyone in attendance for your participation and questions as well. With this, I believe we come to the end of the NISQ webinar series in this part, and I hand it over back to Pascal.
Thank you, Venkatesh, and I will just add my thanks to yours. Thank you to the speakers for very interesting presentations, and thank you to our audience for their questions. And well, this webinar has been recorded, so if you want to replay it later, you will receive the link. And that's all for now. Thank you. Bye-bye.
Thank you.
Thank you, everyone. Bye.